Start off with an anecdote. I went to the K-State 28th annual conference on statistics and agriculture this week because I like being around stat people and a lot of statistics. Believe it or not, a lot of things we do in education and a lot of things they do in agriculture are the same. And while I was there, I got a ping from Google saying someone cited me in a paper. And here's the title of the paper: A Desired Profile of Horse Personality, a survey study of Polish equestrians based on a new approach to equine temperament and character. I kid you not, the book that I co-wrote with Andrew Rupp and Bob was cited by this article right here. Somehow, I'm now big in ag. No, I'm just kidding. First, I go to this conference, and I'm sitting around, people are talking about, like, you know, well, if you've got this control group and you're breaking the back of these swines, you know, you don't want to do that. And next I get this ping saying, look at that, someone cited me in the equine temperament literature. I didn't even know that's a thing. So for those of you who are looking for a dissertation topic and have cats, you might be able to come up with a feline temperament scale. What do you think? All right, so I digress. So tonight is the last class. There is no quiz. Actually, there is sort of a quiz. It's called the teaching evaluation. I'll hand this to you at the end, and then I'll ask one of you to, you know, do what you got to do to make that happen. All right? Okay. Benjamin notes that we have donuts. Anybody would like donuts? Come on up. He just opened them in front of us. He brought them from a previous class. They were trying to bias the evaluations. I'm not. I'm actually trying to bias them badly by handing back a quiz. There's also, this was just left up here, someone's Nutrigrain bar, but it appears to be sealed. So if you want that, it goes to whom the first person who wants a Nutrigrain bar, come get it. But this is also a fun class because you can just sit back and relax. You know the homework is already out there. You know you should see your grade already. You should be able to see what you could get if you make everything turn green. And I have a feeling there's some of you already who made most of them, or if not all of them, turn green, so cool on you on that. If not, tomorrow is office hours from 2 to 4 in room 622. And then next Tuesday will be office hours as well. Once again, homework will be due on Tuesday of next week like normal. And I would ask, I don't believe anybody has late points on homework this year, but could you please not have late points on this homework? That way I can submit your grades fast. But I'll take a look at whomever hasn't submitted yet, and if you haven't, I'll probably email you and say, hey, when's it coming, yada, yada, yada. But is that cool? Everybody got my email? I assume most of you checked your points, made sure you were right where you thought you should be, and looks like nobody's in danger of anything. It's pretty cool. You're kind of where I want you to be. So I made this big deal about the quiz last week, and I was thinking everybody was struggling on the quiz, and yet the grade at the end of class is going to be, everybody's going to be B and above, it looks like. So not the end of the world, because you know what they say about B's, right? Thank you very much. Thank you.
I was going to say they kill people, but...
What? Bees kill people? They do, but bees get degrees. Am I right? Nothing wrong with it. In graduate school, the minimum GPA goes up, right? And actually, you can get by with a C or two, right? With most programs, but in some, they kind of give you threatening letters. There's probation as a grad student, believe it or not. You don't ever want to get there, right? But none of you are going to be in that boat from this class, so I'm happy about that. So I made that. It's like, what's wrong last week? And I should have just like calculated the grades first. I'm like, it's cool. I get it. One of the comments was, hey, we calculated how much the quiz points were. It wasn't worth it. Cool. Got it. Not a big deal. I'm down. All right. So thank you all for your effort on homework and everything in this class. I do appreciate it. I'm continually trying to change things and tweak things as we go forward. So next time I teach this class, whoever knows, I don't know when that will be, but whenever I do teach this class again, it will be better because of your efforts. So I appreciate that. And the good news is I get a course release coming up in the next few years. So I'm even teaching one less course now. Anyway, I don't know if that's good news or not. I like teaching. We're going to talk today, the other bit of good news is the topic Clustering and classification. This is one of my favorite topics. My research area involves a little bit of this. Diagnostic testing is the class I'm teaching next fall. That's this area as well. I've decided it will not have a homework system for those of you enrolled in it. Got another way that we're going to do things next year, but not homework. And the neat thing also about this is not only do you get to hear about this in the class, you can take the high-level overview of it, right? You don't have to memorize it. You don't have to whatever, sort of just there for your own good, for you to enjoy whatever comes from it. Because I know I enjoy it. So we're going to talk a little bit about classification methods. Actually, we're really going to focus on clustering. Believe it or not, there is a difference between the two. The other thing I was going to mention is there is a class on the books in the psych department called Clustering and Classification. It's like Psych 993 or 996. I created that class. I taught it once. I don't think it's been taught since then. So like I do like this topic quite a bit. Maybe we'll hijack that and make it an ed psych class that I never teach. But that would be I have a history of that, right? Make a class, never teach it. The difference, you may hear clustering and classification. They sound like the same thing. The big picture with both of those is you've got objects or people, participants, and you want to put them into groups, right? It's always what we want to do. We want to go put a label on someone. That's essentially what we're doing here. We're going to go label people. If you know the groups ahead of time, what the process is called classification, right? You essentially say, hey, I've got, trying to think of a good example. What's a good classification variable? Someone want to help me? This is kind of an interactive lecture. Race.
High or low?
I'm going to go with neither of those. Let's go with something we can't directly observe. Like,
mastery of a content area.
oh,
Whoa.
okay, that sounds good. Let's imagine we have some type of statistical criteria for what mastery of a content area might represent. And there can be two types of people. They can be people who have mastered the content area, and there may be people who haven't, right? So along comes a person, and you say, hey, you give them some items, or you'll give them some type of survey, or you observe their behavior, and then you take the data that you've collected, and you use some type of math to go and give you a classification to put that person to mastery or not. All right? That's sort of it. You see this all the time. It's usually bad things people classify. I never think of good things, right? Classification usually comes about with like credit risk or terrorist risk. Or it's always the things that nobody wants to talk about. But classification, again, the key in classification is you know the people, you know what their status is. Could it be race? Like if you're sitting there trying to profile someone, right? And you're like, let's see here, right? But that's part of it as well. That would be there. Generally speaking, these are things that we can't directly observe, though. Why is Bernie Sanders and Hillary Clinton and Donald Trump up?
Oh, you know.
And then back over here, I've got Ted Cruz, the Zodiac killer.
Wait, hold on. Worst case, if he sleeps killing us?
I'm just going to put this here. Again, trying to downwardly bias my teaching ratings. That seriously was on the computer over here. Yes. Anyway, I feel very creepy now.
About the ghost in the machine.
Yeah. So trying to classify whether he's the Zodiac killer. Classification, right? Clustering is different. Clustering is saying, hey, I've got these data. Do I have multiple groups of people involved in it? Right? You have no idea the groups ahead of time. So the process of clustering is to figure out the groups. And then once you have said groups, you can go and classify.
I'm
Walter.
getting weird EFA, CFA-like vibes here. Is that like a thing?
That's sort of it.
Okay.
Clustering, generally speaking, there's all sorts of methods for it. But if you don't know the groups ahead of time, that is sort of an EFA exploratory analysis. Hey, I've got data. Do I have groups? I don't know. Sure enough, any method that you use to find groups will find them. So then the question becomes, are they actually valid groups, or are they what we would call spuriously? The classification, having the groups already, is more like CFA, although there are clustering methods that sort of use, say, I know the number of groups, I just don't know their characteristics, so it sort of blurs the line in between there. That's sort of what we do in diagnostic models. Mastery is what we're trying to classify, but we just don't know the rules for what classification happens to be. So, does that help? Getting a good vibe. So, other questions? How many of you have groups in your data? All right. Do you know your groups? Yeah? Sort of. How many of you don't know? That's good. I don't know either. And Megan's smiling because we tricked out one of these a few weeks ago, and it was pretty fun, right? So I'll let you talk about it when we get to the mixture part. But the key to all of this, surprise, Megan's going to give a lecture. Again, further trying to downwardly bias. I'm going to cuss one of you out, too, in front of the rest of you. See all the ways that I can make this work. Anyway, the key with both of these to classification is we're going to see methods that rely on distances. And I'm going to call distances more or less because there's a ton of ways of defining what a distance is. And ultimately, the process of clustering is to figure out sets of people or objects or subjects or whatever that have little distance within a cluster, but that cluster has big distances between them, right? And so this distance is the interesting part of all this. Distance sort of makes all of this run. The more or less part is that there's a million different ways of calculating what a distance happens to be. A distance, you can think about it this way, as the number goes up, the further apart two things happen to be, right? So the further apart they are, the less likely they are similar enough to be in the same group, right? So distance is sort of far apart. The opposite of distance is similarity, right? So the smaller, or the higher the similarity, the smaller the distance gets, right? So one of the things that we can talk about that we've done in this semester that you know very well is likelihoods. The likelihood is a similarity. It's sort of an inverse measure of distance. The higher the likelihood, if I remember, like we have the normal curve, the height of the curve, essentially tells you how close an object or an observation is to the mean of a distribution, right? So that's a similarity itself. So if that distribution was sort of characteristic with the group, we'd want observations that had high likelihoods to be part of that group and low likelihoods elsewhere. Alternatively, we could define distance in a different way. We could talk about a literal distance between points. Or when we got into matrix algebra and multivariate normal, I talked about a statistical distance, the Mahalanobis distance. Is anyone going to name their child Mahalanobis? That's what I always think. Be an awesome name. Mahalanobis is what was in the exponent. It's like the mean, the difference, the square difference between the mean divided by the standard deviation, or the what we call statistical distance. We can use it to classify people, and then that we can think about that in a multivariate space. There's a ton of things. So I'm going to show you a little bit about methods about distances first. I'll give a bonus slide on multidimensional scaling, which is essentially saying, I got a bunch of distances. You know, if you've, so back in the day before we had Google Maps, we used to have actual atlases. Anyone ever have an atlas? I'm practicing, all right? I'm practicing getting old. I'm already old, but getting older, all right? Remember at the back of the atlas, there was this triangular table of distances? Sometimes they would have like distances, like if you have the Atlas of the United States, it'd be distances between capitals of the states. That's a distance matrix. What if you didn't have the map that went with it? Right? What if you didn't have the map of the United States to calculate those distances? Could you recreate the map from those distances? That is what multidimensional scaling tries to do. It says, yeah, you give me the distances, I'll give you the map. Pretty cool, huh? Everything got real tense here all of a sudden. Right? You're thinking about it. It's kind of a fun thing. So I'll give you a slide or two about that. We don't typically do multidimensional scaling anymore, but it does show up from time to time. It's fun to talk about. So do you remember Fisher's iris data? I think homework 2 involved it. There were 150 flowers in these data sets. It all the time shows up in clustering and classification. For whatever reason, Fisher started it, and we're really not inventive, and so we just kind of go with it, right? I don't even know if it's Fisher's data to begin with. Somebody named Anderson's. Anyway, there are 150 flowers. There are 50 flowers from 3 species. It's the toasted, the versicolor, and the virginica. There are 4 measures from each flower, and I actually put a picture up to figure out what these are. Right? An iris has a sepal and a petal. Each of those has a length and a width. Right? So if you have 150 flowers, you take measurements of the petal width and length, the sepal width and length. Those are the 4 observations, and I didn't realize this at the time, but these data are already built into R in the data sets command. That's how frequently they get used. It's like R just said, I'll take the data here. There you go. So, questions? Let's get into distance then. So when you're thinking distance, the key to the classical versions of clustering are picking a distance metric. Right? If you're in a mixture model or a latent class model, the metric is all likelihoods. And then picking the distribution is the key. In the classical sense, there's a ton of things that you have to think about. So for instance, what is the nature of the variables? Are they discrete categories? Are they binary? Are they continuous? What are the scales of measurement? What is the nature of the matter under study? Does it lead to distances? Are you going to talk about distances between people on a psychological instrument? Are there items of a psychological instrument? There's not real physical analogs to those, whereas there are physical analogs to distances between cities or otherwise, right? So all sorts of things go into it. Yeah, Megan.
When you were talking about the likelihood,
Mm-hmm.
that's for an individual person, that's their likelihood is their distance from the mean?
From the mean, it's a similarity to the mean, right? So the higher the likelihood, the more likely they are to come from that distribution, right? So the key is the distance. The higher the number, the further apart you are.
They're not in that distribution.
That's right. In the similarity sense, the higher the likelihood, the more they're like in the center of that distribution.
Okay.
Right? So it's like an inverse distance, or oftentimes we call it a similarity. So, other questions? All right. So let's start with our first one, the Euclidean distance. You probably learned about this one before. I know the math teachers have taught you this, am I right? All right. Anyone else teach math aside from the front two? Been holding down on me all semester. Oh yeah, I sort of did too. Surprise. No, so this is the Euclidean distance. The Euclidean distance is, if you take the sum of the distances, the squared distances between any 2 points, any 2 coordinates, and sum them up, you get this. And we can do this with anything we wish to cluster, right? This could be x, could be 1 variable's observations, and y could be a different one. So this could be like the distance between each flower for sepal width versus sepal length, right? Across all 150 flowers. Or we could do the following. We could say, you know, I just want to get a distance between flowers. Right? Flower 1 versus flower 2. I have 4 observations for flower 1. I have 4 observations for flower 2. X1 will be the first observation for flower 1. Y1 will be the first observation for flower 2. Right? So we can come up with a distance between flowers in that way as well. So anything can happen. Euclidean distance is still Euclidean distance. It seems to be a very standard metric. People understand it. Kind of the distance as the crow flies between 2 points. But it may not always be the best choice. Right? So for instance, I made these slides a long time ago, but I'm borrowing them again. I used to live out there. This is an old Google Map photo, but out here is where my family lives now, in my ancestral home of Sacramento, California, in the Roseville area. If I wanted to travel from Roseville to show off this tourist attraction, this Lombard Street. Have you seen Lombard Street before in San Francisco? The world's curviest street, whatever. I made that for a reason. The distance, as the crow flies, if you were to take the 2 coordinates of these in terms of latitude and longitude and figure out the distance between the 2, wouldn't be an accurate representation for how far it is to actually get there, because as you're traveling, particularly as you're traveling in the Bay Area, you can't go straight between 2 points. You have to go around city blocks. So that doesn't, Euclidean distance doesn't seem to make as much sense there. Furthermore, if you're in San Francisco or any city, hell, even in Lawrence, with the Kentucky-Tennessee thing, right? Which one's going north, which one's going south, right? You have to sort of go a little bit further sometimes to get where you need to go because some streets are one way. So there's other distance metrics. This is a general form of a distance metric. This metric is called the Minkowski metric. Fun name. It's essentially this. There's a difference between 2 points raised, the absolute distance raised to some metric m, and the whole thing is raised to 1 divided by that m. So when m is 2, this happens to be Euclidean distance. If m happened to be 1, this would be an absolute distance, right? Which is sometimes called a city block distance. So how far apart in absolute terms are the points? So this is just to say there's lots of ways of figuring out distance, and once you figure out distance, then you can start to say, how far apart are my objects that I wish to cluster? Now, questions on these metrics. Which one do you use? Use one, interpret it, and then have someone tell you otherwise. So I don't know that there's a good way of doing it one way or the other. Or just put in that equation in your paper and have people just have their eyes glaze over. Skip on. Oh, yeah, that's totally awesome. M equals 2. Fair enough. It is desirable to use distances that behave like distances that we think of in the physical world. So there are some key distance properties, right? So for instance, the distance from P to Q, from point P to point Q, is equal to the distance from point Q to point P. Sounds reasonable, right? If I'm that far to Megan, Megan is that far back to me. Right? The distance between P and Q is bigger than 0 if P is not Q. Right? So unless we're standing in the same place, we have a distance, at least some small distance. The distance between P and Q is 0 if P is equal to Q. And then my last one that's a little bit weird, the distance from P to Q is less than or equal to the distance from P to R plus the distance from R to Q. What? That's a triangle. And that's what this happens to be. If we have this distance R right here, right, we can form a triangle here. What we're saying is that to satisfy, this is something called the triangle inequality. To satisfy it, we need to show that the distance, to have the distances satisfy this, we need to show that this distance is always less than these two. Not all distances follow these rules, which is sort of weird. But the nice thing is, if you use Euclidean or that crazy Minkowski metric that you saw before, it follows it. It's cool. What about binary variables? Well, binary variables, sort of an odd thing. The distance between them can be calculated in multiple ways. One of the ways to do so, something called the Hamming distance, talks about how many times we see difference in the two binary variables, right? So these things can either be 0 or 1. The two places where they're distant, right here, 0, 1, and 1, 0, will be a distance of 2 between them. But the interesting thing with binary variables is that there's only so many they can be apart. They're sort of with 5 binary variables, there's 32 different ways that we could express them, 32 permutations of 0s and 1s. So there's a finite number of distances that you can come with. But that's a nature of a binary variable, or compared to a quantitative variable. The binary variable necessarily has much less information. There's two numbers involved, 0 or 1. So there are other binary distance measures. They're all about the same. So here, let me show you some distances. In R, there's a function called dist. It's built right in. It'll give you a distance. So if I took the flower data, which I'm calling data equals data 02, and asked for method equals Euclidean, it will give me the Euclidean distance between the columns of the data set. Right, so here is my distance. This is the distance between the lengths of each of these observations. And by looking at this, what we'd see is that the biggest discrepancy between variables across all our flowers is right here. The petal width seems to be the furthest apart from sepal length. If I go back to my flower picture, although I'm pretty sure some of the people I went to the conference with could tell me that already. Those irises are part of agriculture. And by the way, so am I. I'm into horse temperament. Anyway, what was it? The sepal width and the petal length, or sepal. Yeah, there was a big difference between them. Honestly, I can't even evaluate whether or not that picture is right. I got that from Wikipedia or from like Google. So, anyone knew irises? Do you know sepals and petals? Yeah, is that right?
It didn't ring right with me, but what do I know?
Man, you know more than I do. Okay, so this bottom plot right here are all the distances in the data themselves. So there's a lot of it, right? So with 150 flowers, that means each flower compared with another 149 others, how far apart they happen to be. All right, so if you do the math on that, this index at the bottom is the distance from all these flowers. And what you'll see, sort of an interesting thing, for each of these flowers as you move along, there seems to be three kind of groups, or three sets of indices. And that in and of itself is sort of the indicator that, hey, wait a minute, there might be things that are similar or not. This distance over here is the Euclidean distance. And so smaller means more alike, right? So there's a set of alike things here and a set of alike things here, and then there's sort of disalike things. So we're flying tonight. Questions? All right. Well then, once you come up with the distance, someone said the following: hey, wait, isn't there groups of flowers there? If I didn't recognize, so part of this figuring out this distance down here is I submitted to it only the quantitative data, right? The 4 quantitative observations per flower. I did not tell it which species the flower came from. So if this were to be the clustering problem we talk about, like so if we went into this and we had 4 variables, like they were in our storage war shed that we that we won by outbidding whomever, and we found these data with 4 variables, and we put them into a distance thing. Well, wait a minute, there seem to be groups of these things. What can we find it? That's the question you're asking. And so if we think about that, the Fisher's iris data provides a real easy data set that have some very distinct classes of flowers based on biological species, I guess. I don't know if they're species, but whatever they are. I don't know biology. Are those species of yeah? Okay. Anyone else do like horticulture or flowers? Anybody?
Or variety.
Can I anoint you flower expert for the room?
Sure.
Botanist, or do you prefer a different term?
I would say floral arranging for my specialty. So.
All right. Make sure you find the species with the biggest sepal width. Okay. So clusterings of objects, as you know, can provide us details. So if you found these data and you didn't know, or better yet, you were studying plants and you didn't know what they happened to be, you would go and observe some of their quantities, and perhaps you'd infer that there might be some type of difference in species between the plants based on these data themselves. And believe it or not, there were 2 talks in Manhattan on that very subject. There were methods for coming up with, if you took a picture of a plant, could you come up with a kind of an image processing algorithm to do the clustering and figure out which species it happened to be? But it was essentially the same thing. Rather than having the same distance metric, it was sort of, plant looks different. Is it a different species? Right? So that is the point of all that. So, what's that?
Did they work?
They were very high level talks, kind of the dare I say, like the DLM version of the learning map. You know, this is our learning map. This is kind of how it could work. They didn't actually show data where it worked. No.
I'm going to say no.
No.
Gotcha.
Yeah, they were very high level talks. They were fine. They were fairly. I like what they were doing. I don't know that they had all the technology in place to do it. I don't know that it was a methodological problem. I'm going to say that much. So, they were grad students who gave the talks. They did a pretty good job, though. So clustering, as we mentioned, is distinct from classification. Classification starts with a known number of groups. Clustering does not. So our goal is to figure out the group structure, and the classical versions of clustering algorithms. This class has been a battle between the old and the new for multivariate, right? There was the classical MANOVA, and then there was the new likelihood-based stuff. And the same thing happens in cluster analysis. There's the classical clustering methods that make very little assumptions about data, and there's the new ones that do make assumptions. And so we're going to take the distances. We may make very few assumptions about the distances in the classical sense. We just want to know how far apart they are, or how similar they are if we're using similarities before we cluster things. Whereas the modern methods in this case use likelihoods, right? Like multivariate normal. And actually, we're going to end with multivariate normal over here. The multivariate normal likelihood makes a very big assumption, right? That the data are multivariate normal. So this is one of the cases where likelihoods start making more assumptions than others in classics. So the clustering problem itself make use of similarity or dissimilarity, right? Likelihoods or distances, to define and group variables or observations. So in our case, we're going to take those 150 flowers and see if we can put them into groups and see what the groups look like. But the problem with clustering is it really creates a ton of technical problems. Think of it this way. If we have n objects, right, so these are the things that we wish to cluster, and we want to put them into k different groups, there is a formula that does the permutation or the combinatorics behind this. It's that. So, for instance, if we had 25 observations that we wanted to put into 4 groups, there's actually over 4 trillion ways that we can do that. That's a numerical nightmare. There are, if you think about it, there's 4 trillion ways. If we exhaust it, if we basically come up with this definition of what a group stands for, and then go through all 4 trillion ways, we can come up with one answer that's the best. But the problem is going through those 4 trillion ways. What if we didn't have 4 groups? What if we had more than 25 objects? That's a tough thing. It takes a lot of time and problem. So that's in theory, the one way to find the best solution is to try each possible grouping. And this is called, this is an optimization problem. Again, we talked about optimization and trying to find the peak of a likelihood function. This is a different optimization problem in that a grouping is a very discrete set of points, right? One way of putting 25 observations into 4 groups. There's no linear continuum that goes with that. And the word that goes with this, the high-level word that sort of the class of optimization this falls under, is something called integer programming. Right? So if you have discrete sets of outcomes, you come up with this simplex that you're trying to figure out the peak of, and trying to permute which group, each observation happens to be. Even the state of our computing now, even though it's catching up to such problems, it's really impossible to expect a computer to come up with all possible permutations of a lot of data into a lot of groups. 25 objects, 4 groups. Not a big problem, right? The thing I was looking at, some of the talks this week, we're looking at, they took a picture of like a plant leaf, and they would sort of figure out dimensions of each of the spokes of the leaf as it went along. And so each leaf would have already how many different numbers. And you could collect tons and tons and tons of leaves. It's not like that. That's just wait till fall, right? So anyway, so rather than using the brute force type methods, which would be permute everything and see what's best, there's a bunch of heuristics that have been created, and those heuristics give rise to a lot of the classics in terms of clustering. They are called heuristics because they're not going to guarantee that the solution that you get, or the numbers that come out of the computer, are the best. But there's probably no way to find the best. So it's hopefully going to give you something that's replicable and stable, even if it's not the best. That's the goal. Sounds terrible, huh? You could do it, but it may not be the best. So what we put into each of these algorithms are the similarities, like likelihoods, or the dissimilarities, like distances. And the result of the heuristic depends on the measure that we're using of each of these. So sometimes we could even put in correlation coefficients. The correlation coefficient, is that if you have a correlation between two variables, is that a measure of similarity or dissimilarity? Think of it this way. The higher the correlation, are the two variables more alike or less alike? So they're more alike. So the higher the number, the more similar they are. That's a measure of similarity, right? Correlation is a measure of distance as well. So what we can do, we're going to talk about a couple of these old-fashioned ways. They're called hierarchical clustering. There's this methods using agglomerative hierarchical clustering. Anyone ever heard the word agglomerative before? Jennifer, from your English times. What's a definition of agglomerative?
Like, stick together,
Yeah.
basically. I'm not good at definitions.
Yeah. Something that's glomming, the word glom, right?
It becomes bigger with each
That's
additional
glomming on, yeah, that's it. It's exactly how it works.
technical definition.
That's that's exactly how it works. That's how these methods work. They essentially come up with a solution that starts and says everybody's in their own group. So of our 150 flowers, we have 150 groups. And step one is to say, now we're going to go from 150 groups down to 149. So we're going to agglomerate 2 flowers into one group. And then the next step from that, this will proceed 150 times until we've agglomerated all of them into one group. So the question then becomes, how many groups in the data? That's a tough thing to tell. But that's how agglomerative methods work. Divisive methods start the other way. They start with 1, and they try to throw out members. Get smaller and smaller and smaller. So we're going to talk a little bit more about agglomerative methods. I just mentioned this. They start first with the individual objects, and each object is in its own cluster, its own group. I'm using the word cluster and group synonymously, interchangeably. So the next step is to figure out the cluster, the objects that are closest together. What is the definition of closest? Well, with 2 objects, it's pretty simple. What's the smallest distance between them, or what's the highest similarity? When we get to groups that have more than 1, though, how do you define if you've got, let's say, a group of 10 and another group of 10, how do you define a similarity from the group itself? Do you define it from average? Do you define it from the furthest apart they happen to be, or the nearest they happen to be? All of those questions give rise to a different type of this method itself. They all come with a different name, like single linkage, or complete linkage, or wards, or all sorts of stuff, where you sort of have to go a little bit further to figure out what is it, what's the rule they have to agglomerate, to combine clusters as they move forward. So, this process repeats over and over again. And so, there we have it. Divisive works in the opposite direction. It says, I'm going to start with 1 group, and I'm going to split it into 2 by taking the object that's most dissimilar to the group and throwing it out. And now for each other object, I'm going to try to parse it into a different group itself. So you go from, the agglomerative starts with as many groups as there are objects and ends with 1 cluster. And divisive starts with 1 cluster and ends with as many groups as there are objects. So kind of a working in forwards and backwards for each of these. So those are our 2 steps. There are lots of ways that we can visualize these. One of the most frequent tools to use is something called a dendrogram. Has anyone ever heard the word dendrogram before? All right, I'm going to pick on Jennifer again because why not? I'm not randomly decreasing your grade. In fact, I'm going to randomly leave it alone. But could you just offer up what does dendro mean?
Jake showed it to me last week. Dendros, trees.
Very good. Jake, have you used a dendrogram before? Yeah?
Right under the bus.
What's that?
Right under the bus for Jake.
What did you use a dendrogram for? Nice. There you have it. Dendro, tree, something. Yet again, agriculture. Telling you. Gives rise to statistics. This is a graph. It looks like a tree. That's basically where this is going. It's going to have a bunch of roots at the bottom, or branches. I don't know how you look at this. Branches or roots, and it'll be broken up as you go forward. The graph itself will have an axis that just has groups, and have an axis that has a distance or a similarity. And where you'll see these groups start to form, or branches come into bigger, twigs become bigger branches, it'll tell you the distance with which they formed, or the similarity with which they formed. So you can talk about, oh, these objects came together in the same group at this distance. So I'll show you how this goes. The first example, before we get into our flowers, I had data from a 1991 study of the Economic Research Department of the Union Bank of Sweden. Sorry, it's more. Agriculture, I'm all over that. Banking, oh my God. Yeah. Money and agriculture, those things both make the world go around, right? And yet statistics is involved in both of them. Anyway, there are a set of variables collected, average working hours. There were 48 cities around the world. They were looking at economic conditions. They were trying to cluster those cities into groups to talk about similarly performing cities in terms of economic conditions. They had the average working hours for 12 occupations. They had the price of 112 goods and services excluding rent, and the index of the net hourly earnings of the 12 occupations. And here is a dendrogram of these cities. On the left are the cities themselves. And the graph itself is trying to show you where the cities come together to form clusters. So if you started over here on the left, you would have all 48? 48 clusters. And so the process of figuring out the first group is to figure out which cluster formed first. And I think it's this right here, Caracas and Singapore. For whatever reason, Venezuela and Singapore formed the first cluster with an average distance between them. In this case, there's only one observation, so it's a single distance that was over here at whatever this number happens to be, a very small number. So then the next question is, where's the second cluster? No, that's a good question. It may be Milan and Vienna, or maybe London and Paris, right? London and Paris, they're sort of proximal. But as you get further along, you'll see that at the beginning, where these clusters are forming have very little distance between them. But as you get further and further and further here, you start to see bigger distances between the clusters. In fact, here you have, if we look at where we have 3 clusters of cities, we have one here, and one here. Right? These 3 clusters all have a distance that seems to be fairly large. And if we look at the cities themselves, Tokyo, actually here, Manila, Hong Kong, Taipei, Kuala Lumpur, Bogota. One of these things is not like the others, right? You've got sort of almost Southeast Asia, although Hong Kong, I don't know if you call that part of it. This is 1991, so it was before Hong Kong was back as part of the mainland, or I don't know, whatever they call it now as part of China. Then you've got this group right here. You've got Tokyo, Zurich, Geneva, Toronto, New York, Chicago, Houston. Again, I don't know, but you've got another group. Then here 3 over here. This next one's. So as you're talking about this here, as I'm starting to describe it, you can see the difficulty in the cluster analysis is just like when we have the exploratory factor analysis. Once you figure out how many clusters you want, and in this case, there's not even that good of numbers. It's like what's the biggest distance? I don't know. If I pick 2 clusters, it'd be all these up here and this little group. I don't know. You have to then, once you pick that distance, you have to figure out what does it mean to be in that cluster. But you can. Anyone ever seen a graph like this? Aside from Jake. And I guess Jennifer too.
Jake showed me one.
Way to go. Anyone else? Don't be like Jake. Come on. Raise your hand. So those are the cities. These are the combinations. Okay. So we mentioned that the most similar objects are grouped together into a single cluster with two. So the next question is, how do we measure similarity between clusters? Right? So how do we go from, like, we started here and we have these two cities, Caracas and Singapore, become one in one cluster. And it's pretty obvious what similarity is there, right? Now, these are the two that either have the highest similarity, if we gave that as input, or the smallest distance. But now it's possible this one cluster right here, there are 47 clusters at this step. So the question becomes, which should we fuse together next? Right? Should we fuse two cities, which looks like it does, like London and Paris? We could have fused a third city into this cluster. Right? So we have to come up with a way of quantifying distance from each cluster now. And that's the hard part of figuring out this analysis that I mentioned just before we got into this. So now we don't just talk about distance to each observation. We have to talk about something about the cluster itself. And that's where each of these methods get their names. So we're going to talk about single linkage, but there's a whole bunch of these. All right, we had all these variables. We could think about what's the average for each of those variables. Right? So the cluster average, if you will. And so any one observation could be compared with that average. But what we need to do is come up with a number that represents the cluster itself, like an exemplar. It could be an average. It could be a median. It could be a centroid, whatever that is. We could use some nearest neighbor. We could use some furthest neighbor. That's sort of what we'll do. How are we doing, by the way? Are you bored? There's less math in this one, right? Is that good? I've always heard that happiness is inversely proportional to the number of equations that show up in a lecture. Unless you're me, of course. I like, yeah, give me the equations. Anyway, so we're going to have this example distance matrix. It means nothing, but it is a true distance. You'll see the diagonal has zeros. That's another way of saying it's a distance matrix. Right? The distance from object 1 to object 1 is 0. That was one of our properties we wanted it to have. You'll also note that it is, the lower triangle is reflected about the top. It's like a correlation matrix. It's just zeros down the diagonal. That indicates that the distance between P to Q is the same as Q to P. And I think these, you can also show that this is, actually all these off-diagonal elements are non-zero, so that's the third property. And for any triplet of these, you could show it meets the triangle inequality as well. But I digress. Single linkage method of clustering combines clusters by finding the nearest neighbor. Right? So it says, oh, look at that. I've got 2 observations in cluster 1. I've got 3 observations in cluster 2. The nearest neighbor is the observation in cluster 1 that has the smallest distance between it and cluster 2. Right? We could have done a different method. We could have done what we call complete linkage, which would be the furthest neighbor, if you will. What's the observation in cluster 1 that's the furthest from cluster 2? Meaning, we combine these, saying that all the other observations we know are smaller in terms of distance. Right? So this is the worst it gets. It must be good. We can put them together. Right? That's sort of a way of thinking of it. So that is single distance. You'll note that any other distance is longer between these 2 observations. So how do we do this with our distance matrix? We take a look at our distance matrix and we figure out the objects with the smallest number. Look at that. That happens to be 5 and 3. So 5 and 3 are now, we're going to start with 5 clusters and we're going to move down to 4. 5 and 3 have the smallest distance. They become a cluster. Right? So now the question is, what do we add to, if we want to add a group, there are now 4 clusters in our data, right? There's the 3-5 cluster, and then there's observation 1, observation 2, and observation 4. So if we wanted to figure out what the minimum distance was between each of these, we could say, what's the distance between cluster 3-5 and object 1? So that would be the minimum between the distance between object 3 and object 1 and object 5 and object 1. So that minimum is 3. Same thing with object 2. What's the minimum distance between object 3 and object 5? That's either 7 or 10. That would turn out to be 7. And finally, the last one is, what's the minimum distance between object 4 and object 3, or object 4 and object 5, and now we see the minimum is 8. All right, so essentially we're going through each of these, and we can figure out which has the smallest distance. The other thing we could figure out is whether or not any of these other distances indicates they should be combined into their own cluster to make 3 clusters. Right? So the distance between object 1 and 2 is 9, 4 and 1 is 6, 4 and 2 is 5, but we know is therefore the smallest number happens to be 3. We're going to pick object 1 and put it into the 3-5 cluster to move a step forward. Right. That's what all this is trying to do. So now, actually, this is the same process. You'll see we have this new distance matrix. Object 1 forms, and now we form a new cluster. We have to ask the same thing. What is the minimum distance between that cluster and each of the others? So we go forward. And we keep going. And this is our dendrogram that looks like, right? We started with objects 3 and 5. Sorry for the small font. They formed at a distance of 2. The next object, object 1, got put into the cluster with them at a distance of 3. And then down here, we see that the next group was formed at a distance of 5, which was object 2 and 4. And then finally, we formed everything out at a distance of 6. So the question you're probably thinking is, how many clusters do I have in my data? Anybody? Does this remind you of exploratory factor analysis way too much? How many factors do I have? Oh yeah, that's scree plot. Yeah, draw a picture. There's lots of math. How do you figure out a solution? Oh, draw a picture. I'm going to summarize like classical multivariate. Yeah, factor analysis is amazing. There's eigenvalues and eigenvectors. How do you know what you're doing? Oh, draw a picture. Clustering, it's amazing. We got all these distances and dendrograms and whatever. How do you figure out how many clusters? Oh, draw a picture. It boils down to kindergarten. Well, my little 1-year-old can draw pictures. Like he paints with his fingers, you know. So no, I don't know. That's a good question. Anybody want to guess? How many clusters how many clusters do you see in this data? Who haven't I picked on this year?
What's the most number of clusters you have?
5. 1 per object. What's the least? 1. Everybody's part of the same cluster. Those are both valid solutions in this process.
3.
3. Megan thinks this right here. Hey, Pete, what do you think? 2. Megan, Pete thinks this right here. Arwen, do you have a guess? 2. How many of you say 2? How many of you say 3? Pete? Megan? How many of you say 4?
Isn't it basically how many ever you can justify?
Yeah! Yeah! It's great. There's groups. So yeah, the process, it goes like this. I've got all this complicated numbers. I create a distance matrix. I make a picture out of it, and then I try to justify my picture. Science. I sound pretty skeptical, don't I? Is this sarcasm? You can see the sense of sarcasm. So complete linkage is the opposite. Sorry, by the way, any questions on that? Does it sound, am I depressing you? Same thing happens. Like, it's hard to tell groups in your data if you don't know what they are to begin with. Right? The data really have to have good signal for. So we could do this in R. There is a method called hclust. The default is the Ward's method. I've forgotten what that is. It's the same type of thing. You don't have to invest a lot of time with it. You can figure it out. Me kind of going, whatever. This is the Dendrogram of our 150 flowers. So here's the height. This is the distance itself. Now, how many clusters do we have? Like, this distance right here suggests a lot of them are very similar. But as we go out, I can see, it seems like a cluster here, a cluster here, and a cluster here. Right? Because this distance right here, where these two clusters form, is a lot bigger than anywhere else below it, right? So do those distances represent the 3 species of flowers? They might. They might actually do that. We don't know. But that's our flower data. But wouldn't you know the flower data are some of the best behaving data in the world? There's very little overlap between flowers. There's so little overlap that most clustering algorithms can even go and say, oh yeah, observation 33, that's the suspect case. How does this algorithm classify it? Right? That's how few it is. Like the R squared for this is through the roof. If your R squared for figuring out groups is through the roof, pretty much any method that you use will figure it out with you. If your R squared is going to be very tiny, any method that you use will have a very hard time finding clusters that are very different from each other. Right? So another thing that you could do, once you form these groups, you can go investigate them. And that's that last line of syntax says, although I didn't show you the plot for it. R will go and plot the 3 groups, and you can take a look at whether or not the groups, you can go and look at the means for each variable. Are the means different from each other? In fact, you can go do an ANOVA. You can tell, or you can do a MANOVA. Put it in a mixed model, please. But you could do that, and it will tell you whether or not the groups are significantly different from each other. And if you do that, then you can get some type of validation. Oftentimes, though, if you were to go and say, I've got, 4 groups. Where did the 4th group come out? I think it's this one right here. Right? If I've got 4 groups, it may be the case that group 4 and group 3 are not statistically different from each other on any of the variables. So is that really a group? Hard to tell. It's significant or not significant. Beats me. Questions? Fun times. Yeah, clusters. You ready for another cool method? There's another cool method. The k-means clustering. Anyone ever k-meaned their data before? I just made that a verb, didn't I? K-meaned my data. K-means starts in a little bit different way. I'm not giving you an example of it because it's sort of silly. It says you have to tell it ahead of time how many groups you have. Right? So let's imagine you start with 3 for the flowers. And you say, all right, I've got 3 groups. So the algorithm starts and takes all of your data and splits them at random into groups with the same number of people. And then it takes the average for each of those groups and the covariance matrix. Right? So now you've got 3 groups, 3 mean vectors, 3 covariance matrices. And then, flower by flower, it tries to figure out which group it's closest to. Now it knows, you had to use that flower to create a mean for each of these groups. So you take flower 1 and you create a distance between it and cluster 1, which it should be in, but it may not be. And take a distance between it and cluster 2 and it and cluster 3. And sure enough, you put it in the group that it's closest to. Oftentimes it uses that Mahalanobis distance, so it's not just Euclidean, but you could use whatever you want. takes a standardized distance between each group. So that repeats for 150 flowers. At the end of that, it recalculates the mean vector and the covariance matrix. Right, so now you've got 3 groups. The mean vector and the covariance matrix probably will have changed, particularly if you randomly assign things. And you do the same process. From flower 1 to flower 150, you put it in the group with the closest mean. And you keep doing this process over and over and over and over again until no one switches. When no one switches, you stop and you say, here are my groups. Group 1 has this mean vector and covariance matrix. Group 2 has this mean vector and covariance matrix. Group 3 has this mean vector and covariance matrix. And these are the flowers in each of the 3 groups. So k-means, kind of an interesting method. It came out in the 1960s. People still use it today. One of my grad school colleagues is like, he publishes on it like pretty much every day. He's probably right now publishing. Probably signing the copyright for him. He's at Mizzou. Do we like Mizzou? Do we hate Mizzou? We're sort of ambivalent these days. Anyway. The thing about k-means that was found at the beginning that you don't see with the Dendogram is that k-means says, hey, I'm going to have 3 groups. 1, 2, 3. Right? It doesn't start with all and go to 1 or vice versa. So because of that, it's very sensitive to where it starts. And if you don't randomly assign your groups at the beginning, you will... Sorry, let me back up. If you randomly assign the groups at the beginning, like we just talked about, pretty much almost, depending on how the size of your problem, you may always end up with a different solution, right? A different endpoint. The question would be: do the means vary a lot from solution to solution? So a lot of times people will run k-means multiple times, say 100, with different starting points, different starting configurations, as we call it, randomly assigning people to groups, to see if the mean vectors change a lot between those 100 times. And then you pick the solution that seems, or the set of solutions that seem to change the least. The problem with k-means is, as it was implemented in SPSS for most of the existence of SPSS, SPSS said it randomly assigned people to groups, but really it didn't. It assigned it based on the order in the data. So to do random assignment, you had to permute your data between doing it over and over again. So I imagine k-means. I haven't looked into it. I don't do k-means. I'm hoping it's fixed by now in SPSS. But the point is, there's problems with it, like everything else. Another problem with it is the following: if you have, I don't have a picture of it for you here. I'll have a picture in the next group here. Here we go. There's biplots or scatter plots of these variables. And you'll see this is sort of the color for it is from a different type of clustering method. But you'll see there are variables in the flower data. There are observations. The observations are the symbols. There are observations from 2 species of flowers that overlap. Right? There's one species that's completely separate from the other 2, and these 2 have a few observations that overlap. In the k-means analysis, those observations get assigned to one of those groups completely. Right? So all of that observation, all of its data is contributing to group mean on one side or the other, depending on where it started randomly. Right? So you don't get a probability that an observation is in a class. You actually just get, this is the class you're in. Thanks. Even if you sort of overlap, if you're not quite, So that's another problem with k-means. So k-means has a few issues that people talk about. One being what we call local optima, lots of solutions to it. One being complete classification. There's no probabilistic classification that goes with it. So, how about we take a break now? I feel like I've bored you all sufficiently. Take a break. And at the end of this, we'll talk about finite mixture models, which is the kind of the modern version, if you will. Started in the 1890, though. Probably not that modern. The more recently implemented than software version of these same type of clustering procedures.